Recording in progress.
Hi, everyone. Welcome to our next major topic in Chem 220, which is an application of what we've learned in chemical equilibrium to systems involving acids, bases, and the reactions between the two. So what we're going to do in this particular video is we're going to introduce the idea of what an acid is, what a base is, and also the notion of pH, as we have begun our titration curves experiment in lab this week, and we'll continue to create those curves next week. So let's jump right in. What are acids? I believe we touched on this a little bit in lab. The answer to this question of what are acids is actually not one that I can give you in just one single sentence, because it depends on what perspective you're using to define an acid. So we have three distinct definitions that kind of vary based on what you're thinking about when it comes to what an acid is. So the first is the Arrhenius definition of acids, which says that these are substances that increase the concentration of H plus in solution when they are dissolved. So I like to think about the Arrhenius definition as like what an acid is by itself alone. So if I were to think about like perhaps a little beaker here, if I were to take some substance, let's call it HA for general acid, and I were to dissolve it in solution, then according to the Arrhenius definition, I would have H plus ions in solution, which would make this substance HA an Arrhenius acid. So the Arrhenius definition, increase the concentration of acidic protons, H plus in solution, what an acid is, like just on its own in the beaker. Up next, we have the Bronsted-Lowry definition, which is really where we as a class are going to be focused on. Like this is going to be kind of the primary lens that we use to think about acids and also respectively bases, because we are going to be looking at what acids actually do chemically, like what acids do when they are participating in a chemical change or a chemical reaction. So according to the Bronsted-Lowry definition, this is a substance that donates H plus ion to something else in reaction. So if the Arrhenius definition is like what an acid is alone, then the Bronsted-Lowry definition is what an acid is based on what it does. Now, this doesn't have to be necessarily technically like a base in the way that you've thought about them from Gen Chem 1, but we'll get into that in a moment. But the idea is a Bronsted-Lowry acid is something that donates H plus. So if I had something like, again, for example, HA reacting with X, if this were to protonate X and leave behind A minus anion, this hydrogen ion donation action here, this protonation, is what would classify this general acid, HA, as being a Bronsted-Lowry acid. Now, this third definition is actually a really interesting definition that we will revisit when we talk about complex ion formation in more detail. So we've actually looked at a bunch of complexes already in this class. We did our iron thiocyanate complexation lab. In our Le Chatelier's principle experiment, we've looked at a complexation and decomplexation reaction. We've also done some practice problems in our equilibrium calculations involving complexation. We're going to talk about like the chemistry of how those complexes are formed further down the line in Chem 220. But why I'm bringing those up now is because we can only understand how those complexes are formed if we understand the nature of this new perspective of what it means to be an acid, which is the Lewis definition of an acid. Now, you've heard of this guy, Lewis. When you think Lewis, your brain is probably screaming Lewis dot structures. That's what I think of. I'm not a fan of those, which is probably why I've got some Lewis dot structure trauma. And as you can imagine, based on the guy that came up with Lewis dot structures, the Lewis definition of an acid is not something that pertains to this like acidic H plus, this acidic proton, but rather the Lewis definition of acids has to deal with what's going on with electrons, right? Lewis is all about where are we going to place electrons in a molecule, right? Treating little electrons as dots. So he also came up with this perspective of thinking about what an acid is according to what its electrons are doing, which actually makes a bunch of sense, especially when you move into organic chemistry and you're thinking about bonds being formed as a result of covalency that's going on, meaning sharing of electrons. So this is a worthwhile definition of an acid to consider. So in the Lewis definition, an acid is a substance that accepts an electron pair and as a result forms a coordinate covalent bond. So it's an electron pair acceptor, which kind of makes sense. This is almost the inverse of like a proton donor, right? Give up the positive thing. And then if we're thinking about what's happening with electrons, like taking in the negative thing. However, we are not just like taking in a negative thing. This is not an ionization process. This is the process of forming a covalent bond. So those electron pairs are being used to create an actual shared electron pair, which is what we call a chemical bond. So for example, if I had some kind of acid reacting with some kind of base or whatever, substance B, if substance B has 2 electrons that substance A can accept to create now A bonded with B, then because this was the substance A here that accepted our electron pair, and as a result formed this covalent bond between itself and B, this would be the Lewis acid. So 3 definitions of acids depending on your perspective. What an acid is, what an acid does, and also what an acid does when thinking about electrons. Like I said, we are going to be living primarily for a moment in the land of Bronsted-Lowry, but we will be talking about Lewis further down the line. So these are acids. Similarly, we can construct some definitions for bases. There are also 3 distinct definitions of a base depending on the perspective that you're utilizing. Again, we have the Arrhenius definition of bases. This is a substance that increases the amount of hydroxide ion in solution. So for example, if I had general base BOH, and then I were to take this substance and dissolve it in solution, make it aqueous, this would generate hydroxide ions in solution, and the presence of those hydroxide ions would make this an Arrhenius base. So again, this is kind of like what it is by itself, what the substance is, what the base is by itself. As chemists, we are interested in chemical changes. So let's talk about what bases do according to the Bronsted-Lowry definition of bases. So these are substances that accept H plus in reaction. So if I go back to the example where I had HA reacting with B, I think it was X before, but I'm going to make it B here just to make it super clear we're talking about a base. I know that HA, the Bronsted-Lowry acid, is going to donate here to B. This will create a protonated BH plus, and then our anion A minus. And because B was the thing that accepted or took in that H plus ion, that is what makes this a Bronsted-Lowry base. Get my color coding going. There we go. And then lastly, we have our Lewis definition, which is, again, with regard to what's happening with our electrons. So the Lewis definition. This is a substance that is the source that donates an electron pair. So this is the source of the electrons that are going to form the coordinate covalent bond. So again, in our example, we had something like A reacting with B that had an electron pair to form now A bonded to B. Because B is the the electron pair donor, it's the source of that electron pair that is what makes up this covalent bond between A and B. This would make it a Lewis base. So very, very similar definitions, just talking about who's either accepting or donating electrons, accepting or donating protons, or who's generating H plus or hydroxide in solution. So then what is it that makes an acid strong or weak, right? Like we know, perhaps recall, in Chem 210 or Gen Chem 1, there was a list of strong acids and strong bases. So there's like 6 strong acids So we've got 3 strong binary acids and 3 strong oxyacids. And then our strong bases were our group 1A and 2A metal hydroxides. So this is something like KOH, NaOH, etc., where the nature of that ion, the cation, matters. So as you go further down, things get a little interesting. So we have something like calcium hydroxide, magnesium hydroxide, etc. These were our strong bases. This is just a list, right? This is just like a thing that you maybe have memorized or are familiar with from Gen Chem 1. This is someone telling you these are strong and these aren't. Nowhere in this list is there an explanation as to why one thing is considered strong versus not. So what is it that makes an acid or a base strong? So the strength of an acid or a base depends entirely on the degree of dissociation of the substance in solution. Meaning, how well does that cation, like that H, split apart from the anion? How well does that hydroxide split apart from the cation? Now, remember, if we're talking about like a degree of dissociation, like this idea of whether we have full dissociation or partial dissociation, maybe thinking back to what we know about electrolytes, we now, as people that understand chemical equilibrium, have a way of quantifying that, meaning we have a way of comparing the strength of HCl to HClO4 by looking at the number that describes that dissociation equilibrium. So this is a dissociation equilibrium. So if we've got a large K, then we have more dissociation, which is what we say is strong. So for example, if we think about this from the perspective of the Arrhenius definition, if I have HA that is dissociating like so in solution, if I have a large K, then I am at equilibrium going to be ion driven or dissociation driven or dissociation favored. At equilibrium, which means that the relative concentration of H plus is going to be large. Hence why we call it a strong acid in this case. So there's more H plus present, better degree of dissociation, larger equilibrium constant for the dissociation equilibrium makes us strong. I could also do something similar for our base. So if I had BOH, that was dissociating into B plus and OH minus. Let's look just for kind of comparison's sake at perhaps if this was a K that was small, this would mean that at equilibrium, I am favoring the molecular version of the base, meaning the hydroxide is present in lesser quantity. So this is a molecular favored dissociation because K is small. So we would then call this weak. So this would be strong acid, weak base in a general sense, looking at these particular examples. Point being, what we call a strong acid and what we call a strong base is innately linked to how good something is at putting acidic or basic particles into solution. So the Arrhenius definition, the more acidic particles you're able to put into solution, the stronger acid you are. Another way of saying that is the larger your equilibrium constant for your dissociation is, the more acid particles are in solution, the stronger an acid you're considered. And the same kind of argument or statement can be made for bases. Now, I said earlier that when we are looking at acids and bases in this class, we are going to be focusing on really the Bronsted-Lowry definition, right? And this is also true for this concept of dissociation. So in our next videos, we are going to answer the following question. What happens when an acid or a base dissociates in solution, meaning in water? Because if you look at all of these little like dissociation equations that I've shown you thus far, I've assumed that we've got like pure acid or pure base existing in its own dissociation, which is not really how we do any of this, right? When we're looking at a solution, we're talking about something dissolved in water. So what is it about the nature of water being present that is going to affect what these dissociations look like, and also how we can kind of like relate and measure and compare the dissociation constants or equilibrium constants of these acids and bases. So coming up next, we will be talking about the weak acid, weak base, or general acid-base dissociation equations. And then after that, we'll start talking about how we quantify acidity by using the pH scale.